Hi, today we're going to talk about the drag forces. Now, sometimes when an object just slides along a surface, like friction or a block sliding down a plane, anything like that, then the force of friction does not change with the velocity of the object. So whether the block sliding down a plane is moving slow or is moving fast, the force of friction will be the same. However, when an object moves through a fluid, then that drag force will depend on several things, including the velocity of the object. This is true on things like air resistance or moving through water or anything like that. So the way that the drag force varies with velocity is very complicated. It depends on the shape of the object, weather conditions, altitude, so very complicated in general. However, for small objects at very low speeds, a good approximation can be made if we assume that the drag force is directly proportional to the magnitude of the velocity, such as this. So drag force is going to be equal to minus v times v. Why the minus sign? Well, because drag forces opposes motion, and here the value b is a constant. This constant depends on the viscosity of the fluid, the size and shape of the object, and other factors. So this equation works very well for small objects that move at a low speed in a liquid. And it also works very well for small objects moving in the air at very low speeds, such as dust particles or something else. Now, for objects that move at high speeds, like airplanes or a skydiver or a baseball or a car, then the drag force or air resistance is very approximated to being proportional to the square of the velocity. Okay? Now, when we talked about air resistance, we talked about a concept that is known as terminal velocity. Terminal velocity is the velocity that an object reaches as it falls through the air and air resistance increases to be equal to the force of gravity. Okay? So let's look at this object and see what we can find out. So here we have an object falling through the air. Right? We have the weight pointing downwards and we have the drag force or air resistance pointing upwards. So if I want to write an equation for the net force acting on this object, then the net force will be equal to gravity minus air resistance, or mg minus vp. So if we continue this equation, then let's look at this object as starting from rest, falling through the air under the sole influence of gravity, and we have a resistive force proportional to v. So we will have our equation being net force is equal to mass times acceleration. And if we change acceleration to the derivative of velocity, then we're going to get something like this, where net force is equal to mass times acceleration. Now, let's keep analyzing this equation. So the object is falling from rest through the air under the action of gravity and a resistive force proportional to v. So what happens to the object as it falls? Well, velocity increases, therefore the resistive force also increases. And what happens to the overall net force? Decreases. What happens to the acceleration? Also decreases. So by going faster, we increase air resistance and decrease net force and acceleration. So what happens when the air resistance is equal to weight? What happens when VV is equal to mg? Well, at this point we arrive to our equation being m times dv over dt equals 0. So that means that our acceleration is equal to 0. And it means that the object is no longer accelerating, which means that the object is falling at constant speed. This constant speed is known as terminal velocity. And once terminal velocity is reached, then the velocity is constant, so that means that the drag force does not increase anymore, and we're left with the term Vv at a set value. Okay, so this velocity is constant until, this velocity is constant. So let's look at this equation and see if we can find out an equation for the terminal velocity of an object. How do we find this terminal velocity? Well, let's see. So we have our equation that says net force is equal to mass times acceleration. So mg minus vv is equal to mass times acceleration. But we know that when terminal velocity is reached, the acceleration is 0. So that means that mg minus vv is going to be equal to 0. So vv is going to be equal to mg. So our terminal velocity is going to be equal to mg divided by v. And this way we can get to our equation in terminal velocity. Right? So how does this change our graph? Now, initially, when we graphed v versus t, then we should just have a straight line just going infinitely to infinity, right? Velocity kept increasing constantly without any limitations. But if we graph this now, our graph now becomes something like this, where velocity will increase, but it will increase at a decreasing rate until eventually it reaches a constant value, terminal velocity. Now, keep in mind that this value or this formula for terminal velocity, mg over v, only works when we have a drag force that is proportional to v. If the drag force is proportional to v squared or v cubed or anything like that, then we will also reach terminal velocity, but the value will be different. The formula to find it will be different. Okay? So, for example, let's see if we can find the velocity of an object as it falls through the air, starting from rest, when there is a resistive force that is linearly proportional to v. Okay? So, let's look at this. So we will have our same formula, right? mg minus vv equals ma. And then we're going to have mg minus vv equals m dv over dt. So now let's pass all the differentials to its corresponding sides. Alright, so we're going to have dt equals m divided by mg minus vv times dv. And then we're going to integrate the both sides of the equation to get rid of the differentials. So the integral of dt from 0 to t is going to be equal to the integral of mg minus vv dv as we evaluate this from 0 to v. So to integrate this, we're going to do an integration by parts, where u is going to be mg minus vp, which means that du is going to be equal to minus v dv, which means that du over minus du over v is going to be equal to dv. Then we substitute back our integrals. We have the integral from 0 to t dt is equal to the integral of m over u and dv, which is times du over minus v. So when we integrate this, we get the integral from 0 to t dt is equal to minus m over v natural log of u. So then we have t evaluated from 0 to t is equal to minus m over v natural log of what was it? mg minus vp evaluated from 0 to v. This gives us t equals minus m over v times natural log of mg minus vv minus natural log of mg. T equals minus m over v times natural log according to the laws of logarithm. This is mg minus vv divided by mg. Okay, and then we have minus vt over m equals natural log of mg minus vv divided by mg. Okay, to get rid of the natural log, we raise everything to e. So e to the minus vt over m is equal to mg minus vv divided by mg. Then this becomes mg e to the minus vt over m is equal to mg minus vv, which means that vv is going to be equal to mg minus mg e to the minus vt over m. So vv is going to be equal to mg times 1 minus e to the minus vt over m, which means that v is going to be equal to mg over v times 1 minus e to the minus vt over m. And this would be how we calculate the velocity at any given time if we're dealing with a drag force that is linearly proportional to b. So we go here right here. And if we want to find terminal velocity, when does terminal velocity happen? It happens after a long time. So what happens after a long time? The term with the exponential would be e to the negative infinity, which becomes 0, and we end up with a value of mg over v, which is the same value that we had found before. All right, so let's see. So objects moving through fluids experience a drag force. Drag force is dependent on the velocity or the velocity square of an object. Terminal velocity is reached when the drag force is equal to the weight and acceleration is zero. At terminal velocity, the object moves with constant speed. Well, thank you for watching and stay tuned for the next topic.